Welcome back. This is CT4333. I am starting from where we stopped from the last lecture, which is we're talking about the instructions and also where we are going to find the operands. Well, each instruction that comes to the CPU needs to tell CPU what operation to perform, what are the operands, and what to do with the results, and also it need to somehow specify the address of the next instructions. Remember from our first class, we said the whole operation of computer is fetch the instruction, execute the instructions. Now, in order to specify the address of the operands, all instruction does, it gives the address to the CPU. It provides the address of the operands and address of where the results needs to go, and then we fetch those from those addresses, the operands. If you're supposed to, let's assume you're supposed to add them up. We add them up, and then we store them at where they are. However, these instructions come in different forms and different formats. They all, in every machine, don't look like each other. So for that reason, these addresses that they come in, it could be, well, if it is address, it means it is in the memory. Somehow it's just the data comes in, that the actual data comes in, or some other form. In that case, usually these could be in these operands could be located in the memory, could be on registers, any of the registers on CPU, could be on a stack machine, and it could be on some special purpose registers. Depends on how that processor has been designed. What I said is based on so far all the processors have been designed. All right, they all usually follow one of the formats that I'm going to show you. And those we are going to call them 3, 2, 1, and 0 address instructions. Meaning the machines that when the instruction comes in, sometimes those instructions they provide 3 addresses. In very rare cases, we have seen instructions come in with the 4 addresses, right? Instruction comes in that holds 3 addresses, or 2 addresses, or 1 addresses, or 0 address instructions. So this classification is based on arithmetic instructions that have 2 operands and 1 results. Here are those 3 address machines. The key issue is how many of these addresses are specified by memory addresses as opposed to being specified implicitly. So let's take a look at it. A 3 address instruction specifies memory addresses for both operands and also the results. So we take the operand 1 and operand 2, we fetch the operand 1 and operand 2 from memory, then we perform the operation and we store the results in a specified memory location. A 2 address machine, usually what happens, one of the operands loses its original value. We fetch 2 operands from those 2 addresses that comes in. That address, 2 addresses that are specified in 2 address machine, meaning the instruction specifies 2 addresses. So we go to those addresses from memory and we fetch 2 of them and we perform the operation. Then we write the results on one of those addresses, which means one of those addresses, one of those operands loses its original value and holds the results. That's called 2 address machine. Then we have a 1 address instruction. In 1 address instruction, usually in CPU, we have a special purpose register, which we call an accumulator. So we go once to the memory, we bring in one of the operands and load them to the accumulator. Next time we go bring the next operands, and we perform, all the operations are performed between 1 register in the memory, in the CPU, and with the accumulator. So if you say add, let's say register R1, what you are saying, you're saying add the content of register R1 to the accumulator and store the results in the accumulator. So these addresses specify only one address. So we go, we use that address, we get the instruction, that content of that address, which is your operand, bring them into memory. If it is the first operand, we load them to the accumulator, then we go back to the memory and you bring them in. So as you notice, depending on the architecture, how the memory is, the processor is designed, we may have to, in order to execute one instruction, we may have to make multiple trips to memory. And this is another reason that the whole computer operation is not based on the CPU or the processor's speed. Then we have a zero address machine. I'm going to show all of these by example so you will clearly understand it. Then we have a zero address machine which uses a CPU register stack to hold both operands and the results, which means it takes the first instruction, first operand, pushes them into a stack, then pushes the next operand, into this stack, and then adds up the two top layer of the stack and stores the results on the very top. So that's called a stack machine, and I have to show it to you by hand so you will see that, so you will understand exactly what I am talking about. The 4 address instructions, hardly ever seen. That's the one that also identifies the address of the operand 1, operand 2, the address of where the results needs to be stored, and also the address of the next instruction. In today's computer, we have a special purpose register called program counter. We usually hold the address of the next instructions right there. Here's the 4 address machine, the way it works. This is the CPU, issues the addresses. Operand 1, we go to this address, we bring in the operand 1, then we bring the operand 2, we add them up, we store the results in here, and then we have the address of the next instructions, which comes from the instruction itself. So add results, operand 1, operand 2, next instruction. You see, this is how it's just instructions formatted. So you have a pattern of zeros and ones for add, patterns of zeros and one for the address of results, and it's address for the operand 1, and address for operand 2, and an address for operand for the next instruction. So 1, 2, 3, 4 addresses are specified. Here is the format, instruction format. The add, then you have 24 bits for the address of the results, address of the operand 1, address of operand 2, and the next instructions. And these are in byte. By the way, this is informed in the bits, but you just add them up 4 times 24, and as you see, it goes to about 96 plus 8. That's 104, and it's a large size in the byte, in terms of the bytes. Here's the 3 address machine. 3 address machine. Only 3 addresses are specified. Results, operand 1, operand 2. The program counter holds the address of the next instructions. So we fetch the instruction 1, the operand 1, operand 2, add them up, put the results. The format of the instruction is you have the add, 8 bits for the add, 24 bits for the results address, 24 bits for the operand 1 address, and 24 bits for operand 2. Now, in 2 address instructions, the instruction comes with 2 addresses only. Add, operand 1 and operand 2. What happens, the results get stored in usually in operand 2 address. So operand 2 loses its original value. So we fetch 2 addresses, perform the operation if it is the add operation, and then store the results there. Then the program counter points at the next instructions. Accumulator, or the one address machine, is very interesting. We have a special register on CPU which we call an accumulator. So always we load one of the operands to accumulator first, and then we bring the other operand, add operand 1, right? And any operation, mathematical operation that's going to take place in CPU, always one of the operand is accumulator. And also the results goes to the accumulator. Then we have to have explicit instructions in assembly language that takes the results and stores them back into memory. Again, as you see, it takes a number of steps. It adds up to the little complication, but at the same time, it's very simple. You have the instruction is very short. It's only 32 bits. Add operand 1 address, and first you go one of these. First you use another instruction. Let's say load. You load one of the operands to accumulator. Then you say add operand 1. So the operand 1 comes in right away, gets added to the accumulator, and the results goes to the accumulator. You see, and this is called the one address instructions machine. Then we have a zero address machine. In CPU, we establish using those registers a stack. Stack means it's like in a restaurant, you see they put the plates on top of each other and push them to using a spring, push them to one little hole, and you always, if they want to add these plates, they add on the top. And if somebody wants to take a plate, you have to take it from the top. So always the last in, first out, right? So you push in, and anytime any mathematical operation is supposed to be done, it takes place in the top 2, and then results is written here. So what you do, you first bring in the operand 1, push him in, it's here. Then you bring in the operand 2, push him in, then operand 1 is here, operand 2 is here. And then you say add, it adds them up, puts the results back right here. We need to do one example. I'm going to do one example, and so you can see exactly how we are going to do this operation. This is the one that you could see. I'm going to use another example from the book so you can see that one easily, and this way you have a better understanding that how this works. Okay, let's say I want to do, we have a 3, 2, 1 and 0 address machines. Okay, let's assume I have an expression in C. It says A is equal to B plus C times D minus E. Okay, I want to show you, basically simulate this one in a 3 address, 2 address, and 1 address machines. In 3 address, let's do it in 3 address. In 3 address, it's going to be add, okay, A, B, C, meaning add content of C to B, store the results in A. Then I say let me see, I think I am doing little different things, and let's see, B and multiply by D. Okay, let me do that. This is your one that I'm going to give you for homework, actually. So let me do the one that it is right here. That's A is equal to B plus C multiplied by D minus E. All right, so that would be add A, I'm adding C to B, and storing the result to A. Then I need to multiply D to this one. So I'll say multiply, D needs to be added to multiply to B plus C, but B plus C is stored in A. So I could say D, A, okay, the movement is from the right to the left, all right? So operand 1, operand 2, and the results. Oops. You see here, C added to B and stored the results in A. Movement is from right to the left, meaning the first one, operand 1, operand 2, and results. Three-address machine. Now, I want to multiply D to B plus C, but B plus C is in A. So D multiplied by A, result goes to A. Now A holds what? B plus C times D. All I need to do is subtract E from that one and store the results in A. So say subtract E from A, store the results in A. This is three-address machine. So in order to execute this one in a three-address machine, how we are going to design the instructions, right? If we're going to do it with a three address, our instruction is going to have three address, then this expression in C, it's going to be translated into three instructions. And this is going to be directly translated using the assemblers to zeros and ones. But we know exactly how long it's going to take to execute this one. Now, how about two-address machine? In two-address machine, we said only two addresses of instruction is going to be identified. And then we're going to use one of those addresses also as operand 2, for example, operand 2's address as the results. So the results will go there. Those machines have a little different format for the assembly language. So you need to pay attention to these, that how I'm doing it. In two-address machine, I'm going to load B to A, right? I'm loading B to A. So A is equal to B. Then I'm saying add A, C to A, and results in A. You know why I'm doing that way? One of the reasons I'm doing it this way is I don't want to lose any original value of B and C, D and E. All right? That's the reason I'm doing it this way. So instead of starting with add C and B and store the B in some place and then say load B to A, I'm doing it this way. From the beginning, I'm loading the B to A, then adding the C to A and storing the results into A. This way, B and C, they keep their original value. Then multiply MPY A, D to A. So D already has B plus C. Now you multiply D to that one. You got that one. Then subtract A, E, meaning subtract E from A and store the results in A. Again, here the movement is from right to left. Now let's do accumulator or one address machine, which is called accumulator machine. Let's see how that one happens. You load in accumulator machines. Usually, this is for the load use this form. That means load. I'll load B to the accumulator. Next, I add C. So C is added to the content of accumulator, and result is stored in the accumulator. So what is the results in accumulator right now? B plus C, because I already had the B in it. And then multiply D. Then you multiply D to content of the accumulator and store the results in there. So accumulator now holds B plus C multiplied by D. Then subtract E. Then I subtract E from the accumulator, results in there. Now I need to take that one and store him in A, location A. Now I say store accumulator in A. So I take him into the memory location A and store him right there. Now let's take a look at these stack machine. That's a little different. The stack machine, or zero address machine, right? The way it is done, we said, here's the machine stack, all right? I'll say push B so I push the B here, so the top of the stack has B now. Then I say push C, so B moves to this part, C is up here, right? It's just like the plates, you're pushing them down. Now I say add, only add. What happens? These two are added, and the results is stored here. So this is gone, this is gone. What do I have here? B plus C. Now I need to push D in there, push D. So B plus C comes down here, and this one has E in it. Now I say multiply. So multiplies B plus C by E and store the results right back here. So I have now E times B plus C. Now I need to push E, E, so this one moves to here, and I have E up here. So here I have B plus C times E, times D. Right? So E is in. Now I say subtract. So B plus C times D minus E comes up here. Right? So now at the end, after this instructions, what do I have here? B plus C times D minus E. Now I say pop A, meaning take this one, pop him out, take him to the memory location A, and store him there. And that's exactly what we wanted to do. So in a 3-address machine, we made 1, 2, 3. We came up with 3 instructions. In 2-address, 1, 2, 3, 4. In 1-address, 1, 2, 3, 4, 5. And in 0-address machine, 1, 2, 3, 4, 5, 6, 7, 8 addresses. And as you see, each one of them now, if we count them in the number of bytes, that tells me how, which one might be better, which one might not be better. Even though those exact numbers doesn't say much, because there are many other situations that we have to be concerned. Number of instructions and number of addresses both vary. For example, here, in 3-address, I have 3 addresses. How many addresses? 1, 2, 3. 1, 2, 3. 1, 2, 3. In here, I have 4 instructions, but 2 addresses. 5 instructions, but 1 addresses on each one. Here, 1, 2, 3, 4, 5, 6, 7, 8 instructions, but how many addresses? 1, 2, 3, 4, 5 addresses. So they all are different in that case. Now, there's another form that it's called general register machines. These are the newest one. In this model, what happens, you identify a number of registers, and then you identify a special purpose register called program counter, and also another register that is not shown here, which is called instruction register. And then CPU issues the instructions, and we go, well, it fetches the instructions and decodes the instruction, understands what's going on, and then goes after those addresses and brings in the operands and adds them up and stores the results. And here, as you see, it says load R8 up 1, which means basically bring in, all right, read the content of the address in operand 1 and load them to register R8. Then it says, for example, in another format, add R2, R4, R6. What does that mean? Movement, again, is from the right to the left. Means add content of the R6 register to R4 register and store the results into R2. So what's happening here, once it reads the instruction fetches in, decodes the instruction, then goes after the operands and brings in the operands and stores them in some of these registers. Then performs the operation. He says, now go add the content of R6 register to R4 register and store the results in R2 registers. And then takes that results, takes it back, and puts them into the memory. And then goes after the next instruction. All right? So this is the newest version that usually is being used. And the real machines are not so simple. Most real machines have a mixture of 3, 2, 1, 0, 1.5 address instructions. A distinction can be made on whether arithmetic instructions use data from memory, or they bring them in, put them in the CPU, some of the registers, and from there picks them up. If ALU instructions only use registers for operands and results, machine type is load store. Latest machine. This means only 2 of the instructions, out of all the instructions that we're going to identify, only 2 of those instructions have access to memory. And the other model is other machines have a mix of register memory and memory instructions. All right, addressing modes. I'm going to stop at this point. I'm going to leave this one for another lecture, but please review those notes, and I'm going to post some homework that I want. Some of them I haven't covered them yet, but I will give you plenty of time. So you start the parts that you know and work on those homeworks. All right. I'll see you on next lecture.